There we go. Welcome to the seminar today, our second to last one for this year, before we wrap it up till September. Our speaker today is Elvira Mulyukova. Hopefully I pronounced that correctly.
Elvira.
She's a postdoc at Yale University, Geology and Geophysics Department, working with Dave Berkovici. A little bit about her background. She got her BS in physics from University of Oslo, Norway, and a master's in science from the same department. And then her PhD in geophysics from GFZ in Potsdam, Germany. Her research topics span, from what I can tell from her CV and a little bit about her research, is LLSVP survival to slab detachment dynamics, lithospheric shear zones, and now she's going after some of the biggest questions in our field of what generates plate tectonics and what's behind it, what are the dynamics. So very ambitious research topics. So we're excited to hear. Go ahead.
Thanks so much. Thank you, Peter, for this pretty great introduction. Thank you for having me and for inviting me here to share some of our research. It's a great pleasure to be here on your beautiful campus. As you can tell from the title, Grain by Grain to Plate Tectonics, I'll be covering quite large range of scales. So I'll focus on the smallest scale, crystals and crystal growth, trying to understand some of the physics, almost atomic scale physics. And then I will see how understanding of those small scale processes help us to understand some of the large scale processes, how rocks deform and lithosphere deform, and eventually maybe understand how Earth's surface deforms. So just a few words. First, the work I'll be presenting did in collaboration with my current boss, David Berkovici. As you can tell from the picture, he can be a pretty scary man, and I'll give you one example. The example is when Dave met Jesse here in London. He stared him down until Jesse agreed to invite me here for the seminar. So here I am, clearly very effective. And the last thing is that I've heard that you're a very diverse group, which makes it particularly exciting to give this talk to you. Please feel free to interrupt me at any time. I structured the talk such that I first give you some very broad scale picture of where our research fits in and some of the big questions we're trying to answer. And then hopefully they'll keep you motivated when I get to the nitty-gritties of the crystal scale physics. All right, enough rambling. No, a little more rambling. Actually, just to set the mood, here's a quote by Goethe. "We must always change, renew, rejuvenate ourselves, otherwise we harden." So Goethe clearly understood what it's like to be a crystal in the lithosphere. If you don't understand anything else from this talk, then take away this. Rocks are made up of grains or crystals, and if you don't do anything to them, they just grow by diffusion. And when they grow, the material hardens. And to weaken the material, you need to do work on it. And just why the material needs to weaken, I will get to you in a second. But essentially, you need to weaken the rocks to have life on Earth. So we'll get to that. All right, off we go. There's no place like home. Planet Earth is quite unique of all the planets we know so far. It is the only planet that we know of that can sustain life. And the complex life, the sort of humans and animals in general, have been able to evolve here because of its long-term habitable conditions or long-term habitability. We have an atmosphere, we have a magnetic field that protects us from harmful radiation, we have liquid water and land mass, and all these things make Earth quite friendly to sustain life. But this, of course, hasn't always been the case. Early in its history, and especially sort of right after one of its major impacts, the Moonforming Impact, that was 4.5 billion years ago, approximately, the energy released by the impact was so large that the planet was largely molten, both its surface and interior. So this is the stage in Earth's evolution that we refer to as the magma ocean. Of course, very difficult for life to exist on this sort of hellish planet. Even after the magma ocean solidified, you still could not sustain life, and that is because magma ocean crystallization would have released a lot of gases or volatiles to the surface, which would create a very thick, kind of toxic atmosphere rich with water and carbon dioxide, potentially, or maybe possibly similar conditions that what we see on Venus today. So something dramatic had to happen, or sort of change on our planet, in order for life to be able to spring out just a few 100 million years after this event. And one of the most important things that needed to happen is that the planet needed to cool. Okay? So Earth cools by mantle convection. It's a convective heat transport, which largely just involves, I have a pointer. Okay, so by mantle convection, we mean that material in the Earth's interior is hot, and as it heats up, it expands, becomes buoyant, and rises to the surface. And then material that is at the surface cools, becomes denser, and subducts down into the Earth's interior. And so to accommodate this up and down motion, this convective heat transport, the material at the surface moves around laterally. So this is manifested as plate tectonics at the Earth's surface, where new material is coming up at mid-ocean ridges, travels away as it cools, and then the cold material goes down at the subduction zones. So this is all good and well, that material that is new, that is coming up and forms this tectonic, so the entire surface is kind of split up into this big tectonic plates. So the new plates that are come up, they are hot and buoyant, and they want to stay at the surface. And once they become dense enough to sink, they should go down. And it seems quite intuitive, but there is one big problem here, or enigma here, that I will explain in a second. So here's sort of a newly forming plate. You envision a mid-ocean ridge here, and new material is coming and is moving away from the mid-ocean ridge as it cools. A very sort of one of the most important factors that determine the evolution of this material is temperature. So the Earth's rocks, their strength is strongly temperature dependent. And so although the plate, as it ages and cools, is becoming heavier and heavier, kind of illustrated here, and wants to sink, it is also becoming stronger and stronger, what we call the thermal stiffening, because colder rocks are stronger and stiffer. So it becomes increasingly harder for the plate, the aging plate, to deform and subduct. And you can, so in a kind of convective setting, you can describe this in terms of competition between two forces. One is the buoyancy force that wants to drag the plate down, and the other one is the viscous resistance to deform and drag the plate down. And you can plot them on this illustrative diagram here, where on the x-axis I have the Rayleigh number. It tells you how strong the buoyant force is. And here you have the viscous resistance, or really the contrast between the cold material and the hot material, with the cold one being stronger. So according to this diagram, Earth plots into this stagnant lid regime convection. This is sort of what we're observing, presumably, on Venus today. What it tells you is that the amount of strengthening due to cooling is way more than the amount of how much heavier the plate is getting. So according to this diagram, Earth plates should not be forming tectonic plates. They should not be bending and subducting. It should just be a rigid surface. So something else in the physics of the materials needs to operate or be at least as important as the thermal effects in order to allow for the material to weaken, deform, and constitute plate tectonics. And you can probably already guess what is the mechanism I'm going to propose for that, and that is going to be the grain size evolution. Okay, so let me get to here. Right, so the hypothesis I will be testing in this study is that one of the ways to weaken rocks is to reduce their grain size. And motivation for this hypothesis comes from a number of observations. Perhaps one of the most important ones is that places on the Earth's surface where you see an exposed plate boundary, so places where the Earth's lithosphere has undergone a lot of deformation, or sort of is observed to be weak enough to deform, such as mid-ocean ridges, these are ophiolites or the shear zone, lithospheric shear zones. Regions that have undergone the most deformation exhibit a strong grain size reduction. So in fact, mylonite, by definition, is a rock that is made up of very small grain size, mylonites and ultramylonites. So rocks that undergo a lot of deformation or appear to be weak appear to also have a very small grain size. This is also supported by laboratory studies, where if you do deformation on rocks, the grain size tend to shrink, and places with the smallest grain size would then be localizing your deformation, will be the weakest parts of your rock. Just a quick example, one of the studies we did earlier this year is this sort of application of how grain size can affect the strength or viscosity of the rocks in a passive margin-like setting. So just an example of a setting within the lithosphere. So this is quickly just an example. On the x-axis, you see time. On the y-axis here, you see the grain size. And on the right, same time. And here you see the viscosity, so how the two are correlated. So this is for conditions that would be representative of lithosphere-like conditions, about 10 megapascal of stress, 1,000 Kelvin temperature. So I'm driving deformation like so. And if you just follow this pink line here, I start off with centimeter-sized grains. And I see, so because of the work I'm doing on the system, I see my grain size shrink down to something like a micrometer scale. This would be sort of very fine-grained ultramyelinite. This reduction in grain size happens over the course of a few million years, so within 10 million years. And associated with this grain size reduction is this sharp drop in viscosity, which goes from something like 10 to the 22nd or 23rd, typical lithosphere-like viscosities, down to something like 10 to the 18th or 10 to the 19th, something more representative of the asthenosphere. So when the viscosity of rock is this small, remember this is all for the same temperature, when the viscosity is this small, we would assume that the resistance, the viscous resistance, is now not too strong, and the material can actually give in to its buoyancy-driven flow, can subduct under its own weight. All right, so I'm diving deeper and deeper into physics. Again, stop me at any time if I'm using any of the terminology that is not familiar. So quickly, to understand how grain size and strength of the rocks, so deformation of the rocks, are related. So what you can sort of understand this process is looking at this type of deformation maps. What I have on the x-axis here is the grain size. I'll be indicating it with this letter R. On the y-axis is the stress, tau. And some of the dominant mechanisms by which rocks deform in the lithosphere and the mantle are diffusion creep and dislocation creep. So if you're somewhere up here where the stress is high or the grain size is large, you're mainly deforming by dislocation creep. In this regime, your strength of the material, the viscosity, is stress dependent. So these are the nonlinear rheologies. If you're down here where the stress is low and the grain size is small, you're deforming by diffusion creep. And importantly, in diffusion creep, it's a linear rheology. However, it depends on the grain size. So this is the setting under which reduction or sort of any change in grain size will affect the rheology of the rock. If you're somewhere here, if you're deforming by dislocation creep, as your grains are deforming, they can change in size. They undergo what's known as dynamic recrystallization. This is sort of grinding down big grains that the rock is made of into smaller grains. So you'll be moving to the left of this diagram. If you start off with very small grains or have very low stress, you are not necessarily recrystallizing, but your grains are growing just by diffusion. In general, both of the processes will be taking place in sort of a larger sample with a grain size distribution rather than just a single grain. So if you're here, you're moving to the right of this diagram. RF here, this is just the field boundary that tells you where the two deformation mechanisms are approximately as important to accommodate the deformation. And so this kind of behavior is relatively well understood, where, again, both processes are taking place, and for a given stress and temperature conditions, when the rate of grain growth and the rate of grain size reduction by recrystallization, when they are approximately in equilibrium, you'll observe some mean grain size. And in fact, sort of geological observational studies use this form of understanding of sort of relationship between grain size and stress to infer stress under which the material was deforming from the observed grain size. This is what is known as the piezometer. Okay? So when the two processes, grain growth and grain size reduction, are about imbalance, you end up at this piezometer. So what we're trying to do is to understand what are the underlying physics that allow us to do this transition. We go out in the field, we can observe the grain size, we can determine temperature based on some independent measurements like mineral assemblages, and to be able to infer the deformation conditions from that, such as stress, we would really like to understand the underlying physics of grain size evolution. So I'm about to dive into the smallest scale that I will talk about, that I will be discussing in this talk. So now we're really getting down to grains. Yes?
Krishkov used to get bothered by subduction and say that if you did beam theory, that huge stress explained by olivine rheology, and that viscosity is inversely
Right.
if you can bend something fast, it's easy to bend. If you try to do it slowly, So are you going to cover that sort of thing? Because
I will not cover bending. I will. We did look into bending specifically for the passive margin collapse theory. The rheologies I'm describing here are ductile rheologies, so this is viscous flow. The beam theory, the bending theory, that relates to the elastic sort of regime. And yes, you're right, sort of it is the short time scale deformation, like what allows the seismic waves to propagate, or in general to accommodate stress by elastic deformation. So what is important here is, if you think of the lithosphere as about 100 kilometers thick slab, say, the elastic behavior will be observed in the first top a few tens of kilometers, so 10 to 20 kilometers. And this elastic thickness varies a little or a lot between oceanic lithosphere and continental lithosphere. But importantly, the elastic behavior is constrained to the top few tens of kilometers. The strongest part of the lithosphere, the one that is sort of the bottleneck for a sort of cross-lithospheric shear zone or weak zone to form, is really within deeper. So it's within the sort of between 30 to maybe 80 or 100 kilometers depth. This is where the lithosphere is still quite cold, so material is cold, but it's ductile. Okay, so this is really, if you look at the sort of kind of the stress tree or strength tree, where you have depth on the y-axis and strength on the x-axis, you see the strength of the rock increase with depth. And when you reach this kind of 30 down to 80 kilometer depth is where it reaches its peak strength. So this is where it's ductile. You cannot easily kind of pump fluids in there because the pressures are too high. You cannot crack it easily because it's ductile and not brittle or elastic. And elasticity is already long past because that remained at the top. So I'll be focusing, and it's a really good point, I will be focusing on ductile flow. These are the only rheologies I'm considering here.
limited up at 55 kilometers.
Right, okay.
That's where,
I'm really happy you brought this up because at the end of this talk, as you'll see, I'm kind of spoiling the surprise here, but I will mention briefly this interaction between kind of high strain rates, large stress behavior, such as an earthquake, so like megathrust earthquakes, and the ductile response of the material that is in the vicinity of it. So I'll get to it. And of course, the two are related. And the brittle ductile transition is also one of the hot topics that we're trying to understand. But I'll mention it a little bit in the end as more kind of a teaser for what's to come in the future. All right, so for now, this will be mostly ductile rheologies. So really, I'm now diving down to the smallest scale, what are grains and what are the physics we're interested in. So grains are really just, these are kind of illustrated here. So grain 1 and grain 2, two different, so a solid material is really just a crystalline lattice. Atoms are arranged in a crystalline lattice. And two different grains are really just two lattices that are oriented with a tilt relative to each other, or kind of at an angle relative to each other. And they're separated by a grain boundary where the atoms that make up the lattices are slightly more distorted. And just by Brownian motion, the atoms will be moving, hopping from one grain to another, and they'll be preferentially sticking to one grain or the other. And how frequently they stick to one or the other grain is determined by the internal energy of the grain, of the free energy of the grain. So if the grain has a lower energy, atoms will tend to stick a little more to that grain. And what sort of on a larger scale, this will be observed as a grain boundary migrating away from the grain with the lower energy. So this is why the grains with the lower energy will appear to be growing. Okay, so now the question is, what determines the free energy of the grains? And there are two main physical properties that I'll be talking about. One of them is the size of the grain itself that determines the grain boundary curvature. If you have a very small grain, it has a very high grain boundary curvature because it's included in sort of highly curved boundary. And it will, a highly curved boundary, it's like with bubbles, will induce a high, effectively pressure or really just high internal energy of the grain. Another property that affects the energy of the grain is the density of its intragranular defects. So if you introduce, say, dislocations, and I will focus on dislocations in this talk, a grain with a lot of dislocations on its interior also has a higher internal energy. Okay, so these are the two properties that control the internal state of my grains. Its size or grain boundary curvature and the concentration of the internal defects or dislocations. Okay. This is these are the two properties I'll be talking about. This is a brief summary of everything I've just said. And later we'll just be doing sort of a more sophisticated way, but of saying basically just this. Grain size and dislocation density. If you're a small grain with a lot of dislocations, you're not a very happy grain. If you're a large grain with a big and relaxed boundary and you have no dislocation in the interior, you're big and relaxed and happy, and all the other grains want to be like you. Okay, so that's pretty much the conclusion here, or the main motivation for the talk. Okay, so now a little more mathy explanation of just that and what this kind of interaction of these forces lead to. I will explain all the physics that enter our model using just two grains. And if you can understand the physics with just two grains, I think it'll give enough intuition to understand what is happening in sort of a large ensemble of grains. Okay, so I'll have two grains, and they'll be characterized by their size and the dislocation density. They can also have different stress in the different grain, and I'll explain to you why in just a minute. So these are the properties. So R will stand for grain size, R1, R2 with the respective grains. Dislocation density is this omega here, and tau is the stress. You don't need to remember all the symbols that will enter my equations, but I'll point out which symbols are important. Okay, so in this mathematical model, we'll be tracking the evolution of grain size. Okay, so this R dot here is the evolution of grain size. Because I only have two grains, I only need to track evolution of one of my grains, because the other one is just given by conservation of volume. Okay. So the grain size is evolving here as a function of surface tension. Or I should say, I'll be interchangeably using squares and circles to refer to my grains, so they're now squares. So I'll have a bigger square and a smaller square, and they're sharing a boundary. Okay, so because of the difference in size or difference in grain boundary curvature, there is a force acting on the grain boundary, like I was telling you with this little atom sticking to one or the other. So this is reflected here. Effectively, it's a surface tension that the larger grain wants to eat the smaller grain because it's a grain with a lower internal energy. Now, the larger grain in this little cartoon here also has a higher density of dislocations. So that opposes a competing force on the grain boundary where the smaller grain with no dislocations will want to migrate into the larger grain. And this is described here. An important parameter to remember is going to be alpha, because the evolution of grain size driven by these two forces cares about how strong is the force associated with the contrast in the dislocation density, as is governed by alpha. Dislocation density itself is changing too. And that is because when the material is deforming, dislocations, what they do is they migrate through the grains, they nucleate and they annihilate and do all sorts of kinetics just to accommodate the strain of the grain. And this is, so there are two terms. The dislocation density is evolving, hence the dot, and it can be increasing or decreasing, or whether it's increasing or decreasing is determined by this parameter A here, and how fast it's doing it is determined by beta. Let me say a few more words on A, as it's important. So whether dislocation density is going up or down depends on A, and A itself depends on stress, to the squared power, to the second power, and on grain size. All you need to remember from this is that the higher the stress, the higher the dislocation density. And the larger the grain, the higher the dislocation density. This relationship here in particular has been kind of robustly observed in the mineral physics experiments, empirical studies on what is happening to the microstructure when the materials is deforming. All right, and the last part is the fact that the two grains can have slightly different stress acting on them. I'm not going to go into too much detail on that, but the reason why we think that different grains can effectively experience different stress is from the following. As I mentioned, the two grains are really just the same crystalline lattice that is tilted relative to each other. So even if you're imposing the same stress on both grains, the slip planes that are accommodating the resulting deformation will be tilted relative to each other. So the slip planes that are moving or sliding will be effectively seeing a different resolved stress onto these planes. And that is why the effective stress seen by each grain that are tilted may be different. Okay, it's not a crucial part of the model, but we're just saying that we're allowing for this small model for this variation to exist. Yes? This one? Oh, sorry, right, I should mention. So this little hat just means it's a grain-specific property. Okay, so I'm not doing it for the grains because it's a grain size, but if it's A with a hat, it means it's a grain-specific property. For main part of the stock, I think all of my properties I'll be using are grain-specific. So I guess I could have dropped it for the slides, but generally, yes, the hat just means that it can vary from grain to grain. Interstitial material? That's true. That is absolutely true. Generally, what we want to do is to understand the behavior of an ensemble of grains, of course, sort of a bigger rock with a large number of grains, and they're sharing boundaries. Generally, we'll assume that there'll be no material in between the grains other than, they're just bordering each other. This is a way oversimplified model. I'm just using two grains as a kind of made-up model just to understand the competition of the forces that are acting on the grain boundaries, but not by no means inferring that this is representative of an actual physical system. Also importantly, so the main motivation for this is to see how the grain size affects the strength of the rocks and the rheology. And experimentally, to determine the rheology, you need to observe a large number of grains. Sort of interpreting rheology of a single grain doesn't really make much sense. So you need to look at the larger scale structure. So this is really just a very simple way to illustrate.
Possible that the grain size more and less interstitial material. This may be a component that
Are you thinking the sort of matrix?
because the rock is embedded in a material that is interstitial. Maybe as a matter of how much the ratio of actual grain to interstitial.
Right.
I'm not advocating that, but it's a factor.
That's true. It's not something we've considered so far. This is a very simple model where I'm only thinking of one material. It's definitely true that in real Earth-like rocks, you'll have kind of other components. Actually, so one of the most recent developments of this grain damage theory, or how the grain size evolves, was sort of a multiple phase model where you have, it's still a solid rock, but you allow for the presence of more than one phase, or say two phases, and also affects the kind of diffusion dynamics between the grains and deformation of the grains a lot. For this work here, it's sort of assuming, like, let's say you have a chunk of olivine, and there is nothing in between other than just solid olivine crystals. Definitely simplification compared to actual lithosphere, but it would. Yep.
We know from experimental lots of isotopes come
Ah.
So this interstitial phase may be negligible in appearance, but may be very powerful.
That's a really good point. No, yeah, no, I appreciate you bringing it up. I'll keep it in mind. This is, yeah, way simpler than that for now. So far, the sort of biggest number of phases we looked at was 2. Typical kind of even lithospheric rocks will have a lot more phases than that, a lot more minerals. We're sort of trying to strike the balance between the simplicity of the physical model that we can actually work with and understand and how representative that is of actual Earth rocks. So it'll be interesting to expand that in the future. So far, just 1 phase. This is somewhat primitive. But the physics are still interesting. And even in that simple model, I hope to convince you that some of the behaviors are still quite complex. All right, so we have 2 grains, and they can grow and shrink depending on their size and the dislocation density. And first, I'll show you a very simple example where we drop the dislocation density effect and see what happens if all you have driving your grain boundary migration is the grain size or grain boundary curvature. So that's very kind of sophisticated animation right here, very satisfying to watch. Basically, as you maybe can expect, you start off with 2 grains. There is no opposing force. So they can start off being almost equal. Sorry, this is grain size here and time, and 2 different colors. So black is 1 grain, pink is another grain, and grain size is evolving just due to variation in grain boundary curvature, none of the dislocation stuff. So you start with 2 grains, they're almost equal, but one is slightly larger. As the larger one continues to grow, the contrast in grain boundary curvature is just growing. The contrast in size is just increasing. And so what you observe is this runaway growth where the slightly larger grain just eats up the smaller grain. Okay, and so the next thing we want to see is I'm going to turn this alpha parameter, the amount to which the dislocation density contributes, I'm going to turn it up a little bit. So here's what happens. The little kind of wheels here, they're my grains again. Now, I start off with grains that are, again, about the same size. Alpha now is non-zero. The large grain starts to grow. Actually, let me put up the dislocation density here straight away. Large grain is starting to grow and eating up the smaller grains, similar as you saw in the previous example. But as the grain is increasing, its dislocation density, this is this omega here, is increasing as well. Until at some point, the force that is associated with the contrast and dislocation density is sufficient to offset the force that is driving the grain growth due to curvature. So contrary to the previous example where you had this runaway growth, you stabilize the grain size at some given steady state grain size here. The example that I chose to show here, we chose this S parameter that tells you how different stresses resolved into each grain. If it was 1, it would mean that the stress in each grain is the same. The 2 grains in this example reach different sizes because the stress between them is slightly different. I could have shown you an example where the stress is identical. It would still be stable grain size, where the 2 grains would just be equal. It just makes for a much more boring plot where it's just a straight line through. One of the main points, yeah? Sorry, I missed the first part of the question.
When you're adding material from the small grain to the big grain, are you generating new dislocations?
Yeah, so generally, there are sort of two parts to answer that question. Dislocation density for each specific grain is described by this equation here. And in general, in this model, does not depend on what is happening to the dislocation density within the other grain. So for each specific grain, the dislocation density will be growing or shrinking depending on the stress within that grain and the grain size, okay, which also would determine the dislocation dynamics. In an actual system, when you have a grain that is growing into another grain because of the higher dislocation contrast in the neighboring grain, it does so by bulging the grain boundary, and this migrating bulge leaves a wake behind it that is dislocation-free. It's kind of like this dilution effect on the dislocation density. We've played with that parameter as well. It does not in this particular model, the dislocation density evolves so fast that we kind of arrive at the conclusion that the dilution effect is not very important. So I don't include it here, but we've looked at some examples that we also included in the paper, I think, just to say that generally the dislocation density should change due to this migration, but this effect is not that big relative to this just nucleation, annihilation, and general migration of dislocations through the grain. All right. So the most important conclusion from this very simple comparison between one grain eating the other or reaching a steady state is that parameter alpha matters. So alpha is the force that is associated with the contrasting dislocations. And so we've looked at a range of values for this parameter alpha. These are my two equations again, and this is just a linear stability analysis for this coupled set of equations. Because the grain size evolution depends on dislocation density, and the evolution of the dislocation density also depends on grain size just by determining the dynamics at which the dislocations are nucleated or annihilated. Okay, so I'm looking at some sort of perturbation from the steady state of this coupled system of equations. What you're seeing here is the different values of alpha, how much the dislocations matter, and here is the grain size. So each branch on this plot represents a steady state solution, or it's a solution of a steady state to this system. For the colors indicate whether the steady state is stable or not. So the first example I showed you, when alpha was 0, you're here and it's red, and red means that it's unstable. What it tells you is you still have a steady state solution where the two grains are exactly equal. So there are no forces driving the boundary back and forth. But just any tiny perturbation from that steady state will lead to this runaway grain growth. Okay, so that's here. When alpha is relatively small, there is no stable steady state to that system. Basically, you'll just have a coarsening, an unimpeded coarsening of grains and hardening of the material by inference. When alpha reaches sort of a critical value, alpha critical here, you now have an emergence of a stable branch, this is in blue, of stable solutions. This means that at this point, there exists a solution where dislocation density is capable of offsetting some of the forces associated with the grain boundary curvature. It doesn't mean the system will necessarily go to that state, because there is still sort of, you can be outside of that valley of stable solutions, but it just means that the steady state exists. If you crank up your alpha even higher, sort of how much you allow for the dislocations to matter, you can reach a set of solutions where mathematically there is an emergence of imaginary components to your solutions, which what it means is that you now allow for oscillations to exist in the system. In simple terms, this emerges because the grain physics, so the grain growth, is governed by diffusion scale processes. So this is diffusion of atoms across the boundary. Dislocations act on their own independent time scale, their own specific time scale of sort of migration and velocity of large-scale defects. So because there are competition between two different time scales, this allows for a possibility of oscillations within the system. I'll show you one of the examples right now, I think. Right, here we go. So for a large enough alpha, this is this sort of up and down. So what is happening here, this another very advanced simulation, this is really just an illustration. You start off with two grains that are about the same size. The one that is slightly larger starts to grow. Actually, this is easier if you can look in the, here we go. So the slightly larger grain starts to grow, but the dislocation density doesn't really have time to adjust to this changing grain size. And so before it's kind of, the grain size just overshoots its steady state because the dislocation density is still a little low. By the time dislocation density has time to catch up, you now have a higher dislocation density than what the grain is happy with, and so it starts to shrink again because now the grain has too many dislocations. Okay, so I'll do this kind of overshooting, undershooting as it evolves towards the same steady state as I showed you in previous pictures. That sums up this two-grain system. I hope I managed to communicate some of the most important kind of behaviors we can see when the grain size, for involving grain size in this kind of very simple two-grain system. Most importantly, you have two driving forces, grain boundary curvature and dislocation density, and they compete. And because of that competition, there is a possibility for a steady state, for sort of some mean grain size that you can observe through time. And I've demonstrated that you can stabilize grains to have different sizes, even for the same stress that is acting on them, mostly because the crystal lattice orientation can be different. And also, we saw this interesting behavior that is associated with the different time scales that are at play, in that the grain size can oscillate as it evolves towards its steady state. The geological implications of this work, I'll get to them in a second. I'm first going to show you quickly how we sort of upscale this system from the 2-grain to an ensemble of grains model. And so that sort of cartoons are over. We're like on a really hard cook. This is now more towards the continuum scale. This is now the largest scale that we can actually use to compare with the experiments and some of the field observations. A warning sign, first of all, now that we're not just tracking each individual grain. Well, actually, let me say this first. Now that we're not just looking at 2 grains, typically the way we address an ensemble of grains is through a grain size distribution. This is what you're seeing here. There's going to be grain size on the x-axis, and on the y-axis, I'm showing you how likely are you to observe that grain size within your ensemble. Mathematically, it's a lot more trickier to work with this sort of continuous distribution of grains rather than just tracking each individual grain. And so just to be able to find solutions to the system or build a physical model, we were forced to make a few simplifications, but this is just our first kind of take at this model. So important assumptions I had to do is that I eliminated the dislocation density time scale. I'm saying that when the grain size is changing, my dislocation density adjusts immediately to its steady state value. Okay, this is just saying that dislocation density or dislocation kinetics are infinitely fast. Okay, it's an assumption. And secondary, I said that the stress that is seen by all of these grains is the same. Okay, so what this means is that in the model with an ensemble of grains, contrary to just 2 grains, I will not be able to, at the moment, to explore this oscillating behavior. But I can still test some of the predictions that we saw from the 2-grain model, as I'll explain in a second. So the mathematical model looks very much the same. Grain size evolution, where R now stands for any sort of population within this grain size distribution. The math looks quite similar. You're now comparing the evolution of a given population to some mean grain size. And this mean grain size is determined by mass conservation. And similar for the dislocation density. Something that pops out from the ensemble model, to go through it, we sort of had to look at more kind of really robust thermodynamic processes. So we're tracking the evolution of energy and entropy within the entire system. And something that pops out is that this alpha really stands for the competition between the energy, gamma D, associated with each dislocation. So energy per dislocation length, and the energy of the grain boundary. So it's more like a surface energy. Okay, so alpha, which is somewhat intuitive, the amount to which dislocation density contributes to grain growth is really the competition of energy contribution from dislocation, gamma D, and the energy associated with the surface. All right. So this is just to convince you that what we learned from 2 grains is some of what we learned from 2 grains is extendable to this more realistic system of an ensemble of grains. An example again, if alpha is 0, this is what happens. You're seeing grain size on the x-axis in both of these plots. This is what's happening to the grain growth rate. When it's negative, it means the grain is shrinking. When it's positive, it's growing. And here is the evolution of the grain size distribution itself. When there is no effect of dislocations, small grains are shrinking, large grains are growing, and I should say, the colored lines tell you different time snapshots. Okay, so blue is early on, black is the initial state, blue is early on, and red is late in the evolution. So small grains are shrinking and large grains are growing, and the small grains are shrinking faster than the large grains grow. So effectively, this will manifest itself in the whole distribution being broadened and shifting towards larger grain sizes. So this is what is known as just continuous normal grain growth. Also, I mean, actual rocks don't have this nice Gaussian-like grain size distribution, but this behavior of shifting towards larger grains and broadening is robustly observed in the experiments as well. So this is just normal grain growth. Do you have a question?
Yeah, what does the typical grain size distribution of a
I actually have some figures that would show it. Sort of quickly depends on the rock. So what mineral physics experiments would normally report on? First of all, it's a very tedious process to look at your sample, and it's done manually. And there are some software to kind of automatize. It's like a sophisticated image analysis tool to do that. We actually, in our lab, try to build this kind of software. But let's say, okay, so one of my colleagues, Jennifer Girard, she would do deformation of MgO or even kind of olivine orthopyroxene systems. So you look at your sample from a TEM or SEM, and you look at all your grains, and you try to deduce your 3D structure just from looking at this 2D plane. And depending on the stress, you'll have some prevalent grain size. So ultramyelinitic conditions, like typical, somewhat higher stresses, would be from like a few microns to a few tenths of microns. This would correspond to stresses that will depend on temperature, of course. How broad it is depends, again, on stress. So it can vary anywhere from a few microns to tens to hundreds of microns.
I guess you said Gaussian-like wasn't realistic, so I was wondering.
Oh, right. No, it'll
that or two populations, or?
Oh, actually, so two.
I was just asking what you meant.
Yeah. Sorry. No, it just means you can probably fit, and not like without being too bold. You can probably fit some Gaussian to it, but it's. I have some figures at the end, but it's actually sorry. Do I have a minute for a little sidetrack? Jennifer and I, so Jennifer is an experimentalist, and I'm a theoretician, and we sit in the same office. And she's working in Shun Karata's lab, and so she's doing this deformation of rocks. And we've looked at some of her samples together and really just tried to get out what is the real grain size distribution. It's been a source of frustration that most deformation studies I've looked at do not report on like your full grain size evolution. And I understand why. It's difficult to fish it out from just looking at your sample. What is problematic is that to get to actual physics, I need to see the full distribution. I cannot, so normally what I'll get reported is the mean grain size. But unless I know what's happening to the variance and the full sample, I cannot test my theory, say. And I'll be illustrating that right here. So we've been trying to do that together and gave this talk together at some point, basically just reaching out to mineral physicists saying, please measure the full distribution, will be very helpful, but I understand why it's hard. So better software potentially would be great. Another little side note is that most of the experiments, also source of frustration, they would report the deformation experiments would be done on grain size range of just a few microns. It can sometimes be within an order of magnitude, so not even a full order of magnitude. So making any form of inferences from it's broadening and shifting to the right, but you're thinking from like 2 microns to 5 microns is a bit of a, but it's difficult. So I understand why it's being done. So within some limitations. We did the same experiments with the grain size distribution as we did for 2 grains. We started at alpha being 0 and increased it sort of systematically. Here, just a simple coarsening case where small grains shrink and the large grains grow. When alpha is a bit larger, small grains can still shrink, but larger grains now don't want to grow quite as much because now they have to compete with this increase of dislocation density. For an even larger alpha, we'll have shrinking of grains that are too big because now the dislocation effect will be stronger, and so it will drive the grain growth back to where you see here would be the steady state. So the way it manifests in the grain size distribution itself, this is the case I already showed you. It's broadening and shifting to the right. If alpha is slightly larger, it's still shifting to the right, but not quite as fast, and it's not really broadening as much anymore. And here, where you reach your alpha where dislocation density is important, instead of shifting to the right and broadening, you're actually collapsing your entire grain size distribution. So all your grain sizes are sort of shrinking down to your now existing steady state grain size. Okay, so this is where all the grains will want to be like that 1 grain size. All right, so this can quickly be demonstrating this. So this is back to what I get reported and what we can compare this theoretical models with. evolution of mean grain size through time and evolution of variance through time. Both of these parameters tell me what are the physics that are governing my grain size evolution. Alpha being 0, this is this dashed line, so I'm just having increase in mean grain size, alpha 0, and increase in variance, meaning it's broadening. If alpha is slightly bigger, I'm still having a smaller increase in grain size, but my variance is not changing very much. And then finally, this somewhat radically different behavior when my grain size is increasing very little, but my variance is actually decreasing. So I'm collapsing my grain size distribution function. So seeing that in actual reported mineral physics experiments would be very helpful to see if there's any truth to it. Okay, I've reached the last part of my talk. Just a few words on what are the geological implications of some of this physics. So I mentioned to you that alpha is an important parameter, and that from when we went through all the physics to derive the grain size distribution model, we saw that alpha is really just the ratio between energy associated with dislocations and energy associated with the grain boundary area. And if I take a typical material, say olivine, in this case just pure olivine, I have these parameters available, say for a given stress, what are going to be these energies. And I have that for the boundary and for the dislocation density with all these parameters. I'm not going to go into detail, but just to say that there are models that can tell me what these energies are. And so what we looked at is what is the critical alpha. Basically, how strong does this parameter need to be in order for the dislocations effect to matter? And this alpha will depend on stress. So you see stress on the x-axis here and critical alpha here. So say for a low stress of about 1 megapascal, still somewhat typical stress within the lithosphere. So at about 1 megapascal, my critical alpha is way high. The alpha I should actually be observing in an olivine-like material, this stress is way lower. So at these conditions, dislocation dynamics that I was talking about just now probably don't matter very much. It only starts to matter when the stresses are relatively high. So this is at high stress, dislocation dynamics are more important, and energy associated with the dislocations are relatively higher. And so the critical alpha would be way lower. And at these stresses, we should now be thinking about the physics associated with the dislocations to determine the grain size. This is, again, taking this model and inferring stress from some of the materials. And the second implication of the study, this is coming back to the earthquake cycles that we briefly mentioned before. So I showed you that for certain conditions, the system can oscillate as it reaches its steady state. And for olivine-like material, again, I'm using same parameters as before. This timescale of the oscillations will be something like a cycle per 1 to 10 years. So this is, on geological timescale, something that will be relevant for maybe an earthquake cycle. Actually, before I get to the earthquake cycle, again, the reason we care about grain size is because it tells us something about the strength of rocks. Before I said how the piezometers we get from looking at the rate of recrystallization and rate of grain growth, and at some point they reach the steady state. The fact that the path towards the steady state can be somewhat complicated and includes oscillations, now we're thinking something like this may be happening, where as you're recrystallizing, you're oscillating, and so you're weakening and strengthening the material in cycles, and you're traversing this map where you deform by dislocation and diffusion creep as your material goes towards the steady state. So geological settings with this kind of physics could be important is, for example, a case of aseismic creep. So the scenario we're envisioning, if you have a sort of large earthquake, so stress, again, needs to be quite high in order for dislocations to matter. So you have an event that can be up to 100, maybe several hundred megapascals of stress. So say high strain rate, this is what's illustrated in this other study here, strain rate, stress, and grain size. So if you have an event where you have a pulse of high strain rate and high stress associated with it, you rapidly grind your grain size down. And then during the stage of the aseismic or post-seismic creep, you're seeing how your material is strengthening back or sort of healing or recovering from that initial pulse. And what the previous study shown before is that you grind your grains down and then they slowly by diffusion start to grow back up. What this kind of oscillatory behavior would imply is that instead of just smooth coarsening, you'll be kind of oscillating or potentially kind of having a characteristic periodic strengthening and softening as you're reaching your steady state. And that, I think, is the last part of my talk. Here are some take-home messages. Most importantly, don't play with Croatia. But more importantly, maybe, I hope I managed to convince you, although I didn't go into the details of rheology. Grain size is an important parameter that controls the lithospheric strength. It evolves, so grain size can change during deformation and can lead to important feedback between how the material is deforming, how the grain size is evolving, and the rate of deformation will depend on grain size, and grain size itself will depend on the rate of deformation because that's the work that it needs in order to change the grain size. The effect of dislocations, the forces associated with the intragranular defects interacting with the forces associated with the grain boundary energy, and the two will matter for the grain size you'll observe at the end and that you'll use to infer the stress for your deforming material. And then I illustrated that there are these different time scales associated with the different physical processes that can potentially lead to some interesting behavior within cycles of strengthening and softening and so forth. Thank you so much for your attention. I'll take questions if there's time.
They obsess about what water does to the rheology.
Right.
Can you, presumably that'll change both the defect energy and the surface energy. Actually quantitatively say how that water would change it?
So, sort of straight out honest, I have not personally looked at the effect of water. Shun Karato has done a lot of work on this. For example, some of the studies that I would know best are probably from Karato's lab. One important component of what water does is that it, in some conditions, let's say lower pressures, I think, it can facilitate diffusion. And diffusion is what controls how easily grains can exchange material between each other. So if you have presence of water, the rate of diffusion would typically be faster. So you sort of, on one hand, your grain growth can be a lot faster with the presence of any fluids. There is a secondary effect, however, is because everything is happening at the grain boundary, presence of secondary or like even sort of fluids in between the grains could potentially also impede the material exchange, and that is because to diffuse from one to the other, you'll need to partially dissolve some of the material from one grain into this kind of fluid in between or by water and to put it into the other grain. This is just to say, I think it could be relatively complicated. It will depend on the solubility of the material in the water, which will also depend on pressure, temperature conditions, sort of how easily that can happen. Last point I want to make on the water. So again, one of the main motivations for this study is to see what is happening to the lithosphere in what we think is its strongest region, this ductile portion. And there, I mean, you can definitely have some kind of watery hydrous phases, but you want the water itself in sort of its liquid form will not be able to penetrate that deep down. So when we think of the effect of water, we'd be probably thinking as more sort of hydrous phases rather than water in the zone.
I was thinking more of just water dissolved in crystal structure.
Right, so more like what you see in. Right, yeah, I, with this model, have not addressed it yet. There is also this, so David Berkovici and Shun Karato, they looked at this water filter across the transition zone, also has a lot to do with how easily water can migrate or like be transported, how soluble it is in general in the minerals. And yeah, the main effect, I guess, comes from diffusion, affects the strength of the material a lot, just also during the diffusion creep. Have not looked specifically at it yet. Yeah. Right. So the my sort of quite naive view of how this can happen comes from the sketch from this Montesian Hearth paper. here. So to do this study of kind of how stress, strain rate, and grain size interact, what they looked at is they have quite simple block model of ductile material underlying a brittle material that is sort of broadly speaking representative of what the cut through the lithosphere or through a plate could look like. So you envision that there'll be a pulse or sort of rapid deformation within the brittle part, and then the deformation within that brittle part will induce stress or kind of work on the underlying ductile part. And so, you know, the stress or strain will be transmitted into that. So it's this sort of setting, like vertically downward, I guess. So you'll have brittle rapid behavior here and some response of the ductile material underneath it.
So would that be like the response?
Yeah, like if you have a slab and let's say it kind of slips, then whatever ductile material you have in its vicinity that can feel those stresses, however easily they can be transmitted, yeah, it would be, I guess, this type of setting. Yeah?
I mean, what would, do you have any sense of?
So it's a really important question. It's very interesting for the seismic cycle. I imagine that would be a quite different behavior, mostly because then you're in the brittle regime. Also because at the plate interface, you're at relatively lower pressures. So then that would be more a system where the approximation of just kind of a bulk material of a single phase where they're really compact together is probably a relatively poor approximation, because here you'll be more rough surfaces with a lot of stuff happening in between the grains. So I don't think I could easily extend this model to like plate interface. That would be more kind of frictional sliding type of models. Yeah. Was there a question there?
Yeah, can you predict how Elvira is likely to change the planets?
So that is a really important question. That's very interesting. It's actually more relevant to the work that we did earlier, so preceding the study, and also a lot of what Dave Berkovici has been working on. So grain dynamics, all this physics are strongly temperature dependent, of course, and also depending on stress. So here's just a quick example. So you have Earth, where the surface is, say, a lot colder than what you have on Venus. Everything else being the same, higher temperature on Venus will have a number of effects. Let's take two components into account: the surface temperature and the size of the planet. Size of the planet will tell you how much stress you can expect from buoyancy, from pressures, variations, how much stress you can expect within your lithosphere or plate, if you have such. And then there is the surface temperature. So temperature affects how quickly grains grow and harden. So even if you had a process there, underlying convection or whichever, to weaken the rock, the rate at which the material will strengthen again will be determined by the temperature. So the higher the temperature, the quicker it strengthens. At the same time, you have the competing effect that higher temperature also means softer rock. And so one of our former studies, this is a paper we published in 2017, we looked at this competing effect of temperature where we compared the grain size distribution within just Earth-like shear zone, how the temperature is changing and how the grain size is changing relative to that. So grain size would tend to be bigger if the temperature is higher because it grows faster, but it would also tend to be smaller because high temperature means more rapid deformation, weaker material, and so smaller grains. And so there are some interesting kind of grain size distribution just based on that. So that's the first effect. Oh, right, and then the stress available depending on the size of your planet. So using this type of considerations, this was a Nature paper that Dave Berkovici published in 2014, where he could predict that the weak zones, the kind of typical lithospheric, localized, plate boundary-like weak zones you would form on Earth, would be more difficult to form on a planet like Venus, just because the temperature is higher and the healing rates are higher. So even if you had something like, let's say, kind of proto-subduction of lithospheric drips, kind of hanging off the kind of mantle, just subducting under, inducing stresses on the lithosphere, deforming it and making it weaker, those weak zones on Earth could be preserved because the temperature is low enough and grain growth is slow. If you had similar process on Venus, which is similar sized planet, the weak zones would heal a lot faster. So by the time you can form kind of an interconnected set of weak zones that could potentially form a plate, they don't form as easily on Venus because they heal too fast.
But would you expect this importance of dislocation? Versus alpha
Oh.
temperature?
I would say yes, mainly because, so this mainly comes from looking at, I have, a deformation map here. So whether you're, here. So temperature would be important for the dislocations mainly because it determines which deformation mechanism your deformation is happening by. So this compliance is here. Sort of that determine the strain rate and thus determine this field boundary are strongly temperature dependent. This is Arrhenius type of law. And so depending on the temperature will tell you whether your dislocation creep is a prominent deformation mechanism, whether the energy associated with the dislocations is high enough. So I would say that's why temperature would matter. We haven't explicitly tested it.
What I'm getting at is, if I understand what you're saying right, then for large values of alpha, healing is not important because it's benefiting from.
Right.
So if alpha is big, then
That is probably true. Yeah, it sounds like it makes sense. It would be interesting to look at sort of explicitly at how, say, steady state or, say how steady state grain size changes with the temperature and this alpha parameter. I'd say potentially yes. Haven't looked at it yet, but it's interesting. Yeah, it would be interesting to see.
Could you apply the same argument that you have for Venus to the early Earth and say how much cooling would you have to have?
That's such a good question, and so that is exactly what we tried to do in this paper on the collapse of passive margins. So first we look at this. So temperature clearly is a very important parameter. We first looked at matching the sort of theoretical model to modern Earth-like shear zones, and just looked at how temperature determines the grain size distribution across the lithosphere, so across the different temperature on modern Earth. And then once we found, sort of to some degree calibrated the theoretical model to that, we tried to apply that, including the time evolution towards that state, for early Earth-like conditions. And the theory we tried to test is the collapse of passive margins. So you have this kind of classical Wilson cycle where you have opening and closing of oceans. And Wilson would have predicted that your subduction initiation, sort of very important point in kind of initiation of plate tectonics as a whole, is how to initiate subduction. Still sort of one of the big, most interesting questions, perhaps, in geodynamics. So to collapse a passive margin, you need to weaken the lithosphere, and how much you need to weaken it will depend on stress and temperature conditions. So we looked at how the rate of cooling and the rate of grain size reduction, given the stresses you have available, say from the underlying mantle that can be hotter or colder, how the two time scales are evolving and whether you can weaken the lithosphere rapidly enough to allow for it to subduct. And so we applied this type of very simplistic model to modern Earth, to Venus, and to early Earth. And there are some variations between Earth and Venus because even early Earth and Venus, I think just because of what we assume for the stress of the underlying mantle. And because, well, Venus right now doesn't really appear to have any, strictly speaking, passive margins. So there are some conditions at which, yes, you could do that. You could significantly weaken a passive margin. Is a much shorter answer to your question. So we applied this model, yes, to an early Earth or Venus-like conditions. What we can do, so grain damage can help. It can facilitate. What it cannot do is to significantly weaken the sort of more shallow part of the lithosphere. But for that part, we could potentially use not use, but so grain damage will help you in the deeper ductile portion of the lithosphere. It cannot help you in this upper few tens of kilometers, and there potentially will need other mechanisms like penetration of fluids or kind of bending, stresses, or brittle behavior. But thank you for that question. That was.
Assuming that the number of grains does not change.
In which system?
That's just two components. You have two crystals, small and big.
Yes.
And that the story is that is always that small and big, the number will never change.
Yes.
So the first simple question comes, what if one component goes to zero? Why is that a forbidden? I worry about the fact that these two component systems are having some truth, but because of the because it is really not representative of the physical truth, that by default, the effect of the third component is being inherited by these two component views. And you keep getting a picture that gives a full picture on the basis of two components, while in reality, the system has at least three components. And we know this as a fact because that's what the rocks are. At least three components.
So
for that reason, I would like the flexibility, mainly because of my understanding of what you just presented. It is just that more than two components. Now the situation of one happens.
yeah. Let me comment on that very briefly. This question makes me think I might have oversold the model a little bit. The main point of the two-grain system is to understand the forces acting on the grain boundary. Upscaling this system to a grain size distribution will need to take into account a lot of other things. First of all, yes, there are many more grains, and you could, in a larger system, the grain number will change because as large grain grow and consume all the small ones. So in the two-grain system, so in the two-grain system, essentially, one of the minerals will never go to zero because it's a continuous model. But it's not, what I'm trying to say is it's only when I try to upscale the system to an ensemble of grains where I'll need to consider this asymptotic behavior. At the point of the model or the range of its application is just when the grain boundary exists. It's larger than atomic scale. So by the time my second grain is being entirely consumed, at some point it reaches atomic scale, but the model is not valid anyway, or just a few atomic spacing or Berger vector's length. So the point of the two-grain model is really just to look at the boundary between two grains. When I say that we're upscaling it to a larger model with many grains, potentially more phases, so far we want to try to, but it's not that we can directly take the conclusions of the two-grain system and apply. Instead, what we did is we started from scratch. When we started to do the ensemble of grains, we had to consider all the thermodynamics. We did integration over the entire continuum space to do this kind of discrete grain model and see how it scales up to sort of more continuum scale model. I had one more point that I think I may have forgotten now, but this is really just to understand what is happening between grain boundaries for the two grains. A larger scale model will take into consideration changing number of grains and with time, maybe more phases. Yeah, great. Thanks. All right. Sorry, I think I went a bit. I know you wanted to finish by. Hi, how are you?
I'm Kyle.
I'm Elvira. Nice to meet you. It's
So you
Elvira,
mentioned-
actually. I think Peter did that. Now everybody's going to remember me as Elvira.
Elvira?
It's Elvira, yeah.
Okay.